Great, thank you, and welcome to the afternoon session on supply-based solutions, innovations, and natural infrastructure. Mark Silberstein will be the chair for this panel, and Mark is the executive director of the Elkhorn Slough Foundation, which is a community conservation and land trust organization working in the Elkhorn Slough in the central Monterey Bay Area. It's one of the premier wetland and wildlife areas in California. If anyone here has not been out to visit, it's something you must do this weekend, I'd say. Mark is trained as a marine zoologist and has worked on the study of conservation of coastal wetlands for 3 decades. Working with a group of community volunteers, Mark developed the land trust function of the Elkhorn Slough Foundation, which is aggressively working to conserve and restore the Elkhorn Slough, one of the last remaining estuarine wetlands on the Central Coast. Mark was also on a team of conservationists that developed a watershed conservation plan for the Elkhorn Slough watershed that led to significant funding for land acquisitions here. So with that, let me turn it over to Mark to introduce the rest of the panel, and thank you all so much for being here today.
Thank you, Forrest. Appreciate it. Thank you. Well, this is a great honor to be with these folks here, and quite an interesting session this morning. I learned a lot, and it is invigorating to start thinking creatively about how we solve this challenge of water. So our session today is titled Supply-Based Solutions, Thinking About Innovations in Natural Infrastructure, sometimes called green infrastructure. And really, green infrastructure, or this natural infrastructure, is just thinking about using natural systems or mimicking natural processes to manage water and our human needs. You'll see from the presentations this afternoon that this approach encompasses diverse solutions to our water challenges and provides, I think, some promising results. The panelists are all deeply engaged in responding to water and water management challenges, and the 3 examples we will hear and discuss include work in the built environment, in this case on the campus of California State University, Sacramento, where Dr. John Johnston has worked with the administration and students to design and implement green infrastructural solutions to runoff and water management on campus. Dr. Helen Dalka is working on farms in the Central Valley and testing ways to increase infiltration to aquifers. And Dale Huss manages a large farm operation here on the Central Coast and beyond, and has worked both on supply side and water quality issues, and has participated in a number of cutting-edge projects. I will introduce our panelists first, and then each one will come up here and speak to you, a little presentation. As I mentioned, Dale is the Vice President of Production and the Managing Partner of Seamist Farms, a graduate of the University of Nevada at Reno. So you can give me some tips on shooting craps and playing cards. He has been active in water resource organizations and agencies for 2 decades. Dr. John Johnston is a professor of civil engineering at CSU Sacramento, teaching water quality and environmental engineering. In addition, he works with the State Office of Water Programs. And Dr. Dalka is working at UC Davis, a professor there in water management and hydrology. So I think we will look forward to hearing from each of you. And we're going to start with Dr. Johnston, who is going to describe to us some of the work he's done at Sacramento State on the campus for capturing runoff and water. So thanks for joining us.
So let me set my timer here. 10 minutes is not much to talk about a 2.5-year project. As explained, I'm with the Department of Civil Engineering. I'm also with the CSU Sacramento Office of Water Programs, which is an independent research center on campus. And so that logo will appear once in a while. But I put it on here because I work half-time for them and because they were the impetus for this project as well. So I want to talk about retrofitting, that's the key here, the Sacramento State campus with low-impact development stormwater devices. And a little bit of terminology in case you're not familiar with this. In stormwater, we call anything that you do to capture or treat the water, we call it a best management practice. Sometimes it's an activity, sometimes it's a device. And if you take a bunch of best management practices and put them together into a design approach that incorporates the BMPs at the site and not at the end of the pipe, we call that low impact development. So what you're going to see here as I talk through is an emphasis on minimizing infiltration maximizing infiltration to mimic natural hydrology, right? And then also maximizing stormwater treatment where it falls, not someplace in some big treatment plant down the road. All right, so here's where we are, Sacramento. You can see the Capitol's downtown. The campus is that little yellow blob out at the edge of downtown. We blow that up. There's the campus. It's about 250 acres, very urban campus. And then we're sitting right next to the beautiful American River. And this is what we do. The water falls on the campus, runs across parking lots and other areas. Can you see it in there? Yeah, it looks kind of dirty going into the drain there. You get a lot of it. We pump it directly into the river. This was a particularly bad day, all this white stuff. It's not usually that foamy. But a typical day is shown down below. I took these samples from the river on the same day that it was raining one day. And the river, you can actually see the ruler there through the water. And the discharge bottle is what the stormwater looks like going into the river. So on campus, our incentives, our opportunities were to improve the beneficial uses of the river, to meet our permit requirements, to recharge groundwater and reduce our irrigation. The campus, even though it's in the middle of an urban area, uses 4 old agricultural wells from when the campus was a peach orchard many years ago. These old ag wells actually do our summertime irrigation. And then for the community, aesthetics, education, and regional demonstration site. So the way we sold this project was as a place where we could build BMPs to meet the new requirements of the Sacramento Stormwater Quality Partnership, which is the local MS4 Phase 1 organization. So we were supposed to show the community what would these look like on the ground, and then go build one in your neighborhood. These are potential treatment sites on campus. We have streets, parking lots, rooftops, and even existing landscaping. You might think that when water falls on your lawn, it stays there, but it doesn't. Especially if you spend 50 years as students tromping across the grass, it's pretty compacted and the water runs off and it carries dirt with it. We were trying to maximize our bang for the buck. I should explain, I don't think I said this. This is all based off of a grant to the state for Proposition 84 funds. And so we had a limited amount of money and we really had to justify their use. So we were trying to maximize the bang for the buck. We hit big drainage areas. We're trying to replace pervious with less pervious with more pervious. We had to tie it into the existing infrastructure. We didn't have dollars to dig up the campus and put down new pipes. And we were trying to promote water-wise landscaping. What am I doing here? Okay. This is just a slide to show you that we did a lot of things. There's about a dozen different facilities on campus, and I'm not going to go to each one, but just several different kinds. So, several different kinds. We did some parking lots where we built bioretention planters. A bioretention device is like a natural soil filter. So it's there on the left-hand side. It's kind of a cross-section. You see that the plants are on the top. There's 18 to 24-inch kind of a soil compost media, and then we capture the water in a pipe at the bottom. That's that dotted line, that dotted white line. So we did. We went out to parking lots. We dug up the parking lot. We put in concrete perimeters, added in the engineered media there, and produced something like this. All right. Curbs are cut on the edges. Cars park all around this, and right in the middle is the existing storm drain. So we didn't want to move that, but we built around the storm drain. If you don't want to put the underlying collection pipe, you can do what's called a rain garden, or if it's long and skinny, we call it a bioswale, an infiltrating bioswale. So all around campus, on the left-hand side, you see the before. Around campus, we have these little narrow lawn strips that are hard to mow, hard to maintain. You don't want to water them in the summer. We said, let's dig that out. dig it down, cut the curb so the water can go in there, and then run across the surface, infiltrate into the soil, and then if it's a big flow, it goes out through that drain that you see right in the middle. We had a street that we wanted to do something like that on, a green street, we called it. The before picture is up in the corner there. The street's to the right. This is the pedestrian way. Again, a lot of narrow grass spaces. What we did is we went in, we cut the curb, we cut the pavement and put in a concrete wall, and then backfilled between the curb and this cut with gravel and overlaid it with permeable pavement. So this is a special kind of concrete. You can take a bucket of water out, pour it on the concrete, and it slips right through it. I have a great video. I didn't bring it with me in the interest of time, but you can find these, Google permeable concrete, and you'll see people blasting the concrete with fire hoses, and the water just disappears underneath you. It's really interesting stuff. So in the end here, we have the permeable pavement on the right-hand side there. That's the PP, and we park on that. Then there's a new sidewalk, and on the left-hand side are a couple of these bioretention cells all linked together in a row. This is our low-cost system. All we did here is to cut the curb, and then we dug out behind it and replaced it with a high porosity mix so that the water would so that we could collect some water and it would eventually infiltrate away. This doesn't have too much engineering, but it also is very, very inexpensive. That's the nice thing about it. When it fills up, the water just keeps flowing by. It doesn't go in the curb cut. The issue about these is you've got to have soils underneath that will take the water. We built 4 of these all in the same street. 3 of them work like a charm, and the 4th one doesn't. And we're not exactly sure why, although we suspect that past construction may have left some material there that is not the same as all the others. We also tried to grab some rooftops. So every rooftop is a rainwater collector. At Sacramento State, in the older buildings, they piped those gutters directly to the storm drain system. So there is no opportunity to put it on the landscape. It just went into the pipes and into the river. So on the left-hand side, that's what you see is a bunch of juniper bushes and a downspout connected to the drain. And what we did is we went in and we cut that drain. And because we were right next to the building, we were worried about infiltrating water directly into the soil and messing up the foundation. So you see at the bottom there a box. So we built a concrete box and we put it in a compost filter. So even though we're not infiltrating the water, we are treating it. So on the right-hand side, you can see the compost filter kind of filled in with plants. This little apron in the front is this valley drain, they call them, that brings the water from the disconnected downspout to the treatment device. And then finally, I told you we actually did some in the middle of lawn spaces. This is one near the Student Union. You can see a couple of construction pictures there. I was really skeptical of this one. This was not my idea. I would have left it out, but sure enough, in a rainstorm, you can see water coming across the lawn and collecting in a spot where we've dug it out and put in permeable soil mixes. So this was a retrofit project. There's a lot of lessons to be learned in retrofit. I'll just share a couple with you. Oh, please don't tell me that was 10 minutes. Oh.
2 minutes.
Okay, so the storm drains are not always where you want them to be. Down the left-hand side, you see that sometimes the storm drains are right where the cars are driving. You can't use those. On the right-hand side, everything has to fit vertically too. I can't move that storm drain. I have to build around it. You think parking lots are flat until you start to try to put something absolutely flat in them, and then you see that they're not. They're sloped, and sometimes these become very big, and you end up having to put in retention walls, which are expensive. We didn't do this, but this was what we found during the design. You find conflicts with other infrastructure. Oh, that one's mine. You'd think that a campus that had been here for 50 years would know where all of its pipes were, but it didn't. So here is a site. You notice there's a communications line, an electrical line, a water line, a high-pressure gas line, an existing light, and a storm drain. This was one of our proposed sites. The contractor would not build this one because of that high-pressure gas line. He just did not want to get close to it. We did find one irrigation line by probing with a backhoe. which means we found it by accident, and gave us a lot of water during construction. And then people are very careful about their trees. I told you we built these three on the side here. We built. Oh, that's not working. That's the wrong button. What did I do? Okay, so all right. So we built a 3-cell storm or bioretention device between these trees. We didn't want to cut pipes through to connect them underneath the trees. So on the right there, you see that we actually brought the pipe out into a box and then over to the next cell. A lot of extra expense to save the tree, but everybody thought that was worthwhile. And then finally, our biggest issue perhaps is if you take out parking spots, you run against your parking authority, who sees each parking spot as a source of revenue. We actually had to have somebody at the vice president's level in the university approve this. So finally, getting toward the end here, costs and benefits. It was a $3 million project. 2.5 came from the state in Proposition 84. The university put up 0.7, mainly in-kind services. The water quality benefits, we are servicing with this dozen sites about 5% of the campus area. We're treating about 11 acre-feet a year. Of that, about 10 of it is actually is infiltrating. If you work that out, over a 30-year period, that's about $10,000 an acre-foot. That's not going to really satisfy a farmer's budget, but this was a project that had a lot of other benefits. We're doing treatment, we're doing demonstrations, but it's also expensive because it's retrofit project, retrofit. We did do some aesthetics improvements, and we did do some education. The last 2 slides here. This is what it looks like yesterday. So the plants have grown up, and they look pretty nice. There's one of our interpretive signs there that were done by a student. And then we did a lot of education and outreach. We did tours, you can see on the bottom. We did a STEM lecture. We did a regional conference with a local agency. We have the signs everywhere. And we even have an app. I'll tell you about the app here next, or almost next. Next steps, has it had any impact? Well, the landscaping people are now starting to do this on their own. So down the bottom there, this is a piece of landscaping they put in. They took out lawn, put in the low water plants, and they disconnected that downspout, which had gone to the pipe. On the right, this is the CSUS master plan. I don't know if you can see the dark green line right down through the middle. That is going to be the new stormwater Hornet Greenway. It's going to be this kind of artificial creek that will collect and treat stormwater on the campus. And so finally, here's a couple of resources. Around here, the Central Coast Low Impact Development Initiative is probably your best source of information for doing this in your town. And if you want to take this tour, that site in the middle, owpcsus.edu/LID, on your phone or on your laptop, you can tour all of these sites. You can get the details, you can see the plants we planted, you can see the retrofit stories and a lot of details. Lots of good information from the comfort of your living room.
Mm-hmm. That's great, thank you. That's great. Well, I think we're going to pivot now to Professor Dalka. Forrest is going to bring up this presentation. And yeah, Lisa reminded me that if you have questions on these presentations, please write them down on these pads. They will be collected, and we will present them to the presenters. Dr. Dalka has been working in the Central Valley on farmlands and ways to increase infiltration into groundwater. So this is going from an urban setting to the farm setting. Thank you.
Thank you, Mark, and thank you for the organizers for inviting me here. This has been a very informative and very exciting panel or forum today. And I'm also going to start my timer just to keep some time for questions. So I will be taking you a little bit away again from the coastal areas, and I'm going to take you back into the Central Valley, and I kind of want to go back a little bit to what John Laird this morning said in the first panel. He mentioned the urgency of thinking about and really developing approaches to better manage our water resources. And so I will be talking about aquaculture groundwater banking, synonyms that you might know this under are groundwater recharge or on-farm recharge. And the motivation for this research has been, as also John was mentioning this morning, the ongoing groundwater depletion that we have in the Central Valley. So here in this graph you can see the groundwater storage in the Central Valley and how it has changed since the 1920s. And we have lost about, in this graph, about 140 million acre feet over the last 90 or almost 100 years. And most of that depletion has actually occurred in the southern part of the Central Valley, in the Tulare Lake Basin, a little bit in the San Joaquin Basin. But so the question is really what has led to that depletion, and how can we manage this depletion in the future? And SGMA, the Sustainable Groundwater Management Act, will really drive much of the actions that we are implementing in the next couple of years. Just to give you some recent numbers, 140 million acre feet in 88 years is an overdraft rate of about 1.6, 1.7 million acre feet per year. This number has drastically changed since 2000. Since 2000, we didn't have many wet years. And so now actually the recent 2013 water plan update, the numbers in there show that during a normal year, we are overdrafting at about 9 million acre feet. And during wet years, which supposedly recharge our groundwater, we're overdrafting at 5 million acre feet. And that is really a trend we need to reverse. And so one of the solutions that are out there is managed aquifer recharge. And there are many, many different types. And the one that my group is mainly involved with is aquaculture groundwater banking, as shown here in those, or illustrated here in those pictures on the right. And the idea here is that we want to flood farmland in the winter using storm flows or surface water when it's available, and spread it on farmland to have it infiltrate into the ground and replenish the underlying groundwater. Why farmland? One of the reasons is the changing climate. As mentioned this morning, we have an ongoing trend, and we're facing a warmer climate, and with that we will have less snowpack in the Sierra Nevada mountains, which stores about 15 million acre feet of water typically in the winter, which is about 1/3 of the water supply that you're using every year. So as the snowpack is melting, more water will come down the mountains quite quickly, which is a problem to manage in surface water reservoirs. And so if you only have, as you might actually know in California, if you only have most of your annual precipitation coming from 6 to 10 storm events that are quite intense and that bring quite a bit of water, you need large spreading grounds to infiltrate this water into our aquifers. And yeah, and the other, I think, advantage that farmland provides is that it has irrigation infrastructure that could be used to move the water from streams to farmland. At least that's the case in the Central Valley. So my group has been involved in extensive research for the past 3 to 4 years. We have 7 experimental sites where we work with landowners to actually test the practice to figure out how feasible is this to do, particularly on land that is planted with perennial crops. We do modeling and statistical analysis, and really the problem or the question of aquaculture groundwater banking is that it involves so many different factors. Location, where can we place the water where it would go into the ground quite quickly? What soil types are needed? How much water is even available for recharge? as already mentioned, cropping systems that are planted on the farmland in the winter might be at risk. You might have that risk that you're losing the crop if too much water is applied. Of course, on farmland, we're also applying fertilizer, so water quality issues are a huge concern. And then also sort of the practical implications. Where is this water going once it's in the groundwater? How can we recover it? Who owns it? Who is going to pay for it? And so those are all open questions. And so I'm only going to give you a little bit a taste of it, just so you get an idea of some of the tools that we have already developed. One of them is the so-called Soil Aquaculture Groundwater Banking Index, which was developed by a soil specialist at UC Davis, Toby Eugene. He has used soil Surgo data and has come up with this index that ranks soils in terms of their suitability for groundwater recharge. So here you will see soils in green have a very high suitability, meaning you most likely will have high infiltration rates and not much will slow down the water on the way through the root zone. This tool is online. I think the next slide has, I don't have a larger font size web link, but I'm assuming the slides will be made available potentially to the, to the audience. So you can see it then in the URL bar. But if you just Google SAGB, you actually will find this web tool, and you can enter your address or location, and you can figure out whether or not your farm or your particular land parcel is suitable for recharge. And the good news is, based on that soil data, on that soil survey, we have between 3 to 5 million acres within the state of California that are actually pretty suitable to do groundwater recharge on. So these are all the soils that we classify as either excellent, good, or moderately good suitability. And again, on this map on the right, you can see roughly the distribution in the Central Valley. More suitable soils are actually located in the southern Central Valley. We have less suitable areas in Sacramento, where actually most of the excess water would be available. So, and that opens, of course, also up the question, how can we move more water down south, where actually also most of the groundwater overdraft is occurring. And so this is going to be my last slide, where I'm trying to summarize what we have figured out so far with our on-farm research and modeling and statistical analysis. As already mentioned, there are about 3.6 to 5 million acres with soils that are suitable for recharge. We've done on-farm experiments on alfalfa with growers, and we have estimated that if alfalfa is grown on good or excellent soils, you can recharge up to 26 acre-feet per acre. So that's a water column that's about the height of this room. And that's a lot of water that can go in, and it went in about 2 months in the winter. We've also done studies on almonds. Here we are a little bit more conservative just because it's a higher value crop. The risk is higher for losing trees, and replacing them would be quite costly. But even here we have applied 2 acre-feet per acre, or 24 inches, in addition to natural precipitation in the winter. And so far, the tree response has been that there was no difference between the flood and the control treatment. So meaning the trees look like they can tolerate additional water in the winter when they're dormant. We've also done statistical analyses, and we have estimated based on, I'm just gonna cancel my alarm. I'm going to take 1 more minute. We've estimated from USGS stream flow data because we were interested in just like seeing like how much water is actually going out into the ocean every winter from these like big peak flow events. And so we have actually estimated that there is about 2.85 million acre feet of water that goes out every winter. And you might remember what John Laird said this morning. He said even during the drought here, we had storm events occurring, and there were 450,000 acre feet that just ran out to the ocean because we couldn't capture it. And we are hoping that we can tap into exactly those flows and make use of them. And just one last word to water quality. For every of our on-farm experiments, we're actually also collecting soil cores, and we look at the soil nitrate before and after recharge events. And so far, the data has been very variable and did not show consistently a decrease in residual soil nitrate after the recharge water was applied. And so the story is a lot more complicated and is a lot more soil type dependent. And so here we are hopefully doing some more follow-up research to really quantify how much nitrate are we flushing with applying additional water, and how much of that would be a risk to groundwater quality. Thank you.
Oh, thank you, Helen. That's really fascinating. You know, I think one of the things that we talked about this morning was looking at multiple ways to try to solve these problems and thinking about different scales. And so already these first two talks, we've looked at very different scales of work. All of this is important. It all has to converge on how we increase supply and quality. I am happy to introduce Dale. I've had the pleasure of working with Dale in the Elkhorn Slough area, where we worked on a wetland restoration project on abandoned farmland. But Dale and his group have been very collaborative and cooperative on tackling some of these problems. So thank you, Dale, for joining us. We had to drag him out of the fields this morning, so.
Yeah, thanks, Mark. And appreciate being here because really a grower's perspective is important, especially since we're farming next to these wetlands and a lot of things come into play. And most folks don't understand what we're dealing with. How do I change these slides, Mark?
This little down arrow advances, and then this little sun is a laser pointer, if you like.
So a little bit about Ocean Mist. We're a vertically integrated grower shipper of the best artichokes and other quality fresh vegetables. We employ around 1,500 employees year-round in all of our different growing areas, in all the different areas related to growing and operations. Certainly, Castroville, California is our base. Coachella, California, where I'm going on Tuesday, we're already planting up there. In fact, I'm going to say that we're probably a half already planted there for our winter spring production. Huron, California, we'll be going here in a couple weeks for fall and spring lettuce production. Oxnard, California, artichoke and celery production in the fall and spring. Yuma, Arizona, and Santa Tomas, Baja California, and the Mexicali Valley for year-round artichoke winter and vegetable production. So, you know, really the opportunities, and we've already done a lot of things here in the Salinas Valley, a lot of things here that we're proud of. For instance, the Castroville Seawater Intrusion Project, which delivers recycled water to the Castroville 12,000 acre area, started in 1998. The SVRP, which is the tertiary treatment plant for that project. The Watsonville Water Recycling Project, I'm the chairman of both of those projects, of the Water Quality and Operations Committee, that delivers recycled water for use in growing vegetable crops in both the Pajaro and the northern Salinas Valley. There's things going on right now with groundwater replenishment. There's a plant that's going to be built in Marina where water from the Blanco Drain Wreck Ditch, as well as industrial wastewater from the city of Salinas, and waters that aren't being used in the wintertime, will essentially be processed and put back into the aquifer in the Seaside Basin for later withdrawal for use. That's not online yet, but it will be. We bought the nitrate harvester online. It was an idea, essentially, it's like your water softener in your house. This essentially uses potassium. It takes the nitrate out of drain water and captures on a resin, just like what your water softener does. It takes the calcium out of your water at your house, and then it's stripped off later with sodium chloride, with sodium. Well, here, the nitrate was later stripped off using potassium, so the result, what our hope was that we would get a high-quality fertilizer, potassium nitrate, for reuse in our fields. Now, it was a great idea. We spent a lot of money on it, but it just didn't work out for a lot of reasons we didn't anticipate. You know, fouling of the membranes and the plugging of the filters and just one thing after the other. It doesn't mean the idea is going to go away. We're actually on the same site. We're actually going to put a new unit in that uses denitrifying bacteria to remove that nitrate. And I actually expect someday, in the not too far distance, we'll be dropping packs of bacteria into these tiles that will reduce or take out this nitrate. I believe that will happen. And then, as Mark says, we've been working with the Elkhorn Slough. I've been working with Mark now for 20 years, and the Central Coast Wetlands Group on wetland development projects around our properties. So, again, in 1996, the Elkhorn Slough Foundation wetland project at Seamus Farm to Sandy Ranch, the treatment of runoff before entering the Morro Coho. 2016 PG&E Wetland Project, collaboration with the Central Coast Wetlands Group for treatment of runoff before entering the Morro Coho. 2016 Ocean Mist Bioreactor, treating water, drain water, before it went into the DeSanti wetland property. And we're currently working with Ross and the Central Coast Wetlands Group to create a wetland on 35 additional acres that we own adjacent to the Elkhorn Slough Foundation. And part of that, things that are going on there, that I call them the two Ps, plastic and pavement. We're down here at the bottom of the watershed, and all the water is pouring off this pavement, and all the water is pouring off this plastic, and we're also involved in growing strawberries, by the way, ends up at us. And we are underwater deeper year after year. We have no control of that water. There's no way to take care of it. And it's there on top of our crops. We've lost a lot of money dealing with that. This is a picture of the nitrate harvester. As you can see, this drain here along one of our ranches. The water in the drain is actually pretty low here. We had to dam it up on the other side to get enough water. We need 50 gallons a minute to go through it to really process it right. And it's you can see the resin tanks there. And then the tank on this side here is actually the potassium nitrate that will later be used to strip that. It's still in use. We can turn it on and get it going. It's just the problems to maintain it are pretty unbelievable. This is the DeSanti lands here before, Mark took it over. And I never thought their water would stay in it. I mean, in the wintertime when we got a lot of flood, I'd say, yeah. But usually by midsummer, the water's gone. But look at it today. And, you got this water that's coming off drain water from our properties, our farmlands, that's being in there. And as it winds through the wetland, it actually, you see the sandpipers out there poking around, right? Really pretty. There you go. And this is the bioreactor here that I was talking about that's going on here, where the water is going through a series of stages of treatments, and then it goes back into that DeSanti property. So all efforts are being made to clean up the drain water, look at ways to do it as efficiently as we can. And you can see here that you got M1, M2, M3. M1, we're 45 more or less part per million nitrate in, and by the time you get to M3, which is the far site, you're actually below drinking water standard. So you're in real good shape there. Now, here again, people have to understand, this is where most people don't understand what we're dealing with, because the value of our crops that we're growing on these lands surrounding these wetlands, an acre of lettuce, $5,000 an acre before you harvest the first head. Artichokes, $6,000 an acre before you harvest the first artichoke. Strawberries, $25,000 to $30,000 an acre. And so when we start looking at wetlands and having them around, you have food safety issues. In other words, who likes to open that bag of spinach and find part of a frog? Okay, well, when you have wetlands around you, guess what happens? They end up in your crops, whether you want to or not. You can put silt fences up, you can do this, you can do that, but the reality of it is, in real life, that's not what happens. You have animal intrusion in those wetlands. And so looking for ways to mitigate that's very important. Because the last thing we want is, that Dale wants to do is get a call from food safety saying, guess what? We can't harvest that spinach because we found something in there. And it came out of that wetland. And so communication. Buffer strips, you got to have 35 feet with the the Leafy Greens Marketing Agreement, the rules. And then, like I was talking about, food safety. But increased regulation, and I just want to bring this up because it's impossible almost to comply with the regulation anymore. It's so complicated what the regional board and the State Water Resources Control Board is making us do. It's hard to even understand it. And I go back to the 2 Ps. You know, you're supposed to control your discharge, but guess what? You can't. And it all ends up on us. And so how does that play out for the future and how that's going to be dealt with? It's very important questions. I believe having these wetlands around our properties down here in the lower valley is a key part of that solution to that problem. Finally, I've got down here a trust, because I guarantee you that, you know, on both sides it happens. Where you have some people, everybody wants to lie a little bit or a lot, depending on who you are, to get your end to the finish line, no matter what it is. And so if I talk to Mark and he tells me something, and we sit down and we say, okay, how are we going to do this here to keep the geese out of our lettuce? Okay, because they're filthy. Geese are filthy. They can take out 2 acres of lettuce just like that. Guess what else they do? They crap all over the place. Anybody that has geese or has geese around them know that. Well, that's a food safety issue. I don't say that I like seeing them fly on their way to their next nesting ground. But the fact of the matter is, we can't have geese in these wetlands, and so they're designing these wetlands. You don't need, 5 feet of water in these wetlands. You can have shallower pools so that the geese don't land there. The sandpipers are fine. They don't bother us. Other wildlife are fine. They don't bother us. But things like geese, they have to be taken into consideration. And that trust is when we're talking to Mark or we talk to anybody else, and we're telling him our concerns, and he's telling us his concerns. Very important. Communication and trust. Just finish off with my final slide there with, a lot of native grasses and the pickleweed and everything else that's going through that's in these treatment wetlands. And they are pretty things to see, and really proud to have them and be a part of working with Mark and his team. Thank you.
Well, thank you for your questions. I think, I'd like to take a couple of minutes to think about the panel. Look at this. Oh, my gosh, we're going to harvest. This is going to be a good harvest of questions. I think one of the things that strikes me about all the conversations today, and certainly with these panelists, is that, we look for zones of convergence, that where solutions are productive is where you have converging interests. And I think the discussions about how we manage things both in the urban setting, I think it was brilliant to do this on a campus, to do the work you've done at the State University, where you're engaging the next generation. You're engaging students on how do you do engineering that encompasses these fundamental issues. It all boils down to water, as far as I'm concerned. And so you're really working on educating the next generation. The creative thought about using farmland in the wintertime to infiltrate all that water otherwise passing us by. I mean, I think there's some really interesting convergence there. And obviously some critical questions about not impacting crops in a negative way. And I think the work that you described, Dale, and just knowing the things we've done with you, I mean, this is a strong zone of convergence where we have the potential for cleaning water up, cleaning tile drain water coming off fields, getting nitrogen down almost to nothing, getting some at least incremental recharge, although these aren't the best soils for recharge, but also getting wildlife habitat. And I think that there's got to be this kind of flexibility and room for discussion and compromise. I think geese are a problem. And so Dale was extraordinary in figuring out solutions to keep the geese out of the crop. At the same time, he's encouraging us, and his partners at Sea Mist Farms, Ocean Mist Farms, are encouraging us to do this. So this is where it gets fun and interesting and challenging. We got to figure out ways to reduce nutrients coming off farm fields into waterways. So there's a whole ecosystem part of this equation we haven't dug deep into. We have to do that. These wetlands help do that, but they create these other challenges. And so managing that is really, I think, where the rubber meets the road going forward. But one of the questions I guess I have for the panelists to start is to maybe reflect on what you see as the most promising opportunities for expanding this idea of green infrastructure and the use of green infrastructure for both improving water quality and water supply, groundwater recharge. But maybe we just go down the line, starting with John. Any thoughts on, in the work you're doing, how we can expand that?
Well, I painted a kind of a disappointing picture, I think, with the costs and the volumes, and as you look at the field, people are starting. These kinds of data are coming back in, and they're saying, look, there's different ways of doing this that are a lot more promising. If you design your natural system, your bioinfiltration into your development when you start it, the costs are like a tenth or less, right? You incorporate these ideas into your original design. In established areas, people are moving toward more regional systems. So instead of putting a little bathtub-sized thing in everybody's on the end of everybody's block, you go to the edge of the neighborhood and you put in something like a small lake or a pond that can act as the infiltration. That's much more cost-effective. You build into the existing drainage. And in Los Angeles, where they're, of course, highly urbanized, I was at a conference last week, and they were showing pictures of digging up city parks, putting in concrete vaults underneath that become infiltration basins. See 10-foot high concrete tanks with open bottoms, and then putting the park back on top. The park doesn't go away, yeah. It's just underneath the park. And so they can capture millions of gallons from big areas and infiltrate them in a much more cost-effective manner. In fact, there's agencies in the Los Angeles area who will pay $1,100 an acre foot for every acre foot of stormwater you put into the ground. So that encourages people to try to do things.
I think as a grower who's been involved in these issues for some time, I think it's getting the regional and state boards to understand and recognize the fact that we're doing things. Because right now they don't. It's like you have this and it's like, okay, big deal. And what they don't realize is that we're doing these things not just to benefit ourselves, but also other growers and landowners and other folks where this water is coming from. And so there has to be some sort of a credit given to those of us that are doing things. And I'm not saying everybody can do something. The other side of it is I've thought about a nitrogen credit, kind of like a CO2 credit. But I just don't quite know how that would work. I've thought about it. I've given it some thought. When I started thinking about it, we got this nitrate harvester going. Well, how could that work where you as a grower are removing nitrate from this drain water either through biological systems like what we're talking about or through some other way, and cleaning that up. And how could that work? And I think there's some opportunity there. It just requires more thought and brain power.
Yeah, I think for the groundwater recharge that we're doing in the Central Valley, I mean, it will have essentially really a whole range of benefits. Not only would it help addressing, some of the 6 undesirable results that the Sustainable Groundwater Management Act has to address, such as seawater intrusion, land subsidence, water quality, lowering of the groundwater table, loss of groundwater storage, and loss of these groundwater-dependent ecosystems. So if you refill your aquifer and you reconnect the groundwater back to stream beds and our river systems in the Central Valley, it would potentially have the benefit that we can have more base flow in the summer, and we wouldn't have to do reservoir releases to sustain flows for our aquatic species. It, I think, can also provide a climate adaptation tool to mitigate some of the loss of snowpack and managing these big storm flows that are predicted, at least by climate modelers. But one other aspect that we are also currently investigating is whether or not groundwater recharge near disadvantaged communities would provide a benefit to their water supply and water quality issues. And there are a couple examples, very positive examples from Tulare County that have already shown that this is actually a good solution for some of those communities. So we are hoping we can quantify that a little bit better and maybe make that like a role model for many other communities.
I think I'm going to, I have some more questions for you, but I'm going to read some of the questions that you submitted. And so here's a question for Dale. Your photo of the Desante looks like the water isn't percolating. Is it?
The water on that piece, and I'm surprised a lot of things about that, but I'm sure it is, but it's just very slow. It's just very slow. And so it's just very sticky, heavy. In fact, we tried to farm down there 30 years ago, and the first time it rained, even at all, it was over. You couldn't get in there. I mean, you might walk down there, but you'd walk out with 50 pounds on each foot because that's how sticky that dirt was. So it's percolating, but it's just very slow.
And, I might just say, sort of taking off my facilitator hat, because we worked with Dale on that project, that the main goal of that was not percolation, because we knew that those had heavy clays. Those were wetland soils that were not permeable. But the primary function was twofold. One was habitat, the other was water quality, so nutrient reduction. And so in that sense, that worked. We've been working on other projects in the Elkhorn area, particularly in the Sandy Hills above Elkhorn Slough, where there's good recharge. And one of the things that we've been able to do as a land trust is look at some of the really steep eroding slopes around the wetland, and where there were marginal lands and production wasn't good, farms were being abandoned. We've been able to secure those, purchase them, and in some cases reconfigure the farm footprint to something that we felt was more sustainable. In the process of doing that, on the 4,000 plus acres that the nonprofit owns and manages, we have taken about 700 acres out of production and restored it. There was a couple of outcomes of that. One is that on the average, those crops are using 3 acre-feet of water per acre of crop per year. I round up as an executive director. I use executive director statistics. I typically round up. That's about 1 million gallons of water per acre per year. And so the math is fairly simple. 700 acres means that 700 million gallons of water is staying in the ground in one of the most heavily overdrafted aquifers on the Central Coast. And so that's part of balancing the equation. At the same time, we've been able to revegetate those hills so that we're increasing capture and recharge. That is not a solution for prime soils, prime agricultural soils. But again, we look for convergence. So here was a place where there is high conservation value, marginal lands that were causing erosion and other problems, and a chance to really kind of help balance the water equation. So that was a long-winded answer to the question about the Desante. So watch out. Okay, here's a question for Helen. How willing were the growers to receive floodwaters, and describe the process to incorporate projects?
Yeah, that's a good question, and that definitely has changed over the research period. So when I wrote one of the first proposals, and I was actually looking for a lot of help from farm advisors, since for the University of California, they are our arm into the community. And so I actually had one farm advisor in Yolo County who came to my office and played me a couple of voicemails. And they were not positive. They were not positive at all. They were a lot like blaming that this could only be an action implemented by Sacramento, and who had that crazy idea. And but that was in 2013, and then the drought became more severe. And then all of a sudden, groundwater recharge looked like a really good idea. So yeah, and often enough, you always have a few progressive farmers in your community that want to take that risk first. And so it's essential to find them, to work with them. They set examples. We have one almond grower that we work with. He's also a board member on the Modesto Irrigation District. And every time he walks into a meeting with his irrigation district board or with the city, you know, farmers just come up to him and say, like, are the trees still alive? How is it going? Do you see any effect? And often enough he says, like, well, so far, at least on my farm, it looks pretty good. And so word is spreading, and that's all I can hope for, because I think that's getting at that trust that you're mentioning. You can't implement these sort of risky practices if there is not a trust basis to really trust into the science, and also into the outcomes of the data and the research that we're doing.
I think that's interesting, that how ideas and practices spread. Daniel Mountjoy is here from the organization Sustainable Conservation, and has been working with growers on similar kinds of projects. So I think the idea is spreading. Hopefully the water will spread too. There's a couple of questions for John. These are two linked questions. The question is, how durable is permeable pavement? Does it have weight restrictions? And a second question is, how expensive is permeable pavement versus conventional pavement?
It's quite a bit more expensive. I don't think it's your first choice. It's a choice where you want a nice surface, you want a plaza. For example, there's a neighborhood in Davis that's proposing to cover a street and make a neighborhood plaza out of this stuff. The cost is about 3 to 5 times what regular concrete is, and regular concrete is a lot more expensive than just pavement. With durability, it will support all the weights if properly designed and installed. That's not an issue. It will not support high traffic impacts. So Caltrans looked at it for a little bit, and other people, it says it will hold a truck in a parking situation, but it won't hold a truck traveling at 65 miles an hour. It tends to break up. It's not as durable as regular concrete.
Thank you. Okay, for Dr. Dalka, 2 questions. First, what response does banking recharge have on biological communities, or maybe what impact does it have on banking and recharge? You know, how do wildlife, bugs, or birds respond?
We are actually working with the Audubon Society and Blue Point, who have a high interest in groundwater recharge because it might actually provide a potential habitat for waterfowl. We haven't really established a formal project to really test this, but some of the projects that we've done on alfalfa and to those of you who are alfalfa growers, you probably know that alfalfa is already providing quite a few wildlife benefits for various species. So there could be a potential additional benefit for doing groundwater recharge. However, I'm going to say this, the experiments we've done so far, we are not flooding fields for extended periods of time. Some of you might have seen pictures from Don Cameron's farm, Terra Nova in the Central Valley, grapes being underwater for 2 months, really continuously. This is not the practice that we have tested. We really just apply the water using normal irrigation practices, flood irrigation in a couple events. So the benefits from sort of the flooded area that you might get from those events is actually fairly small in time. So I don't actually know really how birds might spot that when they are flying over the field. That would really have to be like a snapshot find.
Okay, well, I think a couple of more questions here. And I think this may be for John. Let's see. This is a question about how many gallons of water do self-flushing toilets and sink use? And is there a cumulative sense of how effective they are at modifying things? This may not be something that you experimented with on campus, and so you may or may not have data on that. But
Self-flushing toilets, you mean the kind that have the little sensors on them so that every time you move, it flushes? I've been thinking about those recently myself. I don't know. It occurred to me last week when I was at an event like this where this was happening all the time.
Right.
And I thought, I need to get a student to measure this. So
right.
I
sort
don't
of
know.
that is a, we sort of automated not only the technology for measuring water use on farms, but sort of metering out when you're standing there. And,
I can maybe add one sentence to that. UC Davis, as part of that challenge to reduce potable water use, was also looking into the sanitary needs of water. And these self-flushing toilets, they are popular because students don't have to touch the levers and there's no disease risk from that. But actually, we have decided to take most of them back out because of the ghost flushing. Because many self-flushing toilets have the tendency to just like flush whenever there's movement spontaneously, and that really increases the water use.
No, that's interesting. Ghost flushing, I got to remember that. Let's see, a couple of more questions here. So again, for John, please speak to considering stormwater treatment and capture at the beginning of a construction versus retrofit in terms of cost and effectiveness. I think that you described the fact that retrofitting these projects can be very costly.
That's right. And so I mentioned earlier, if you are incorporating these into your original drainage system, and if you're ever in Davis, there's a community called Village Homes, which was very famous for a long time for solar power in the 1970s. But they also incorporated this kind of low-impact development before we even had a name for it into their whole community. And so they don't have big drain pipes. They have little gutters. They have spots everywhere across the community to capture the water and infiltrate it into the soil. And it's tremendously less expensive. If you catch it at the beginning, you're avoiding most of the costs that I was showing you. And then you're saving extra because you're not putting in that big concrete drain system that you would have otherwise.
That makes sense. And I think one last question for Dr. Dulka. Can you clarify, do you expect to see less residual nitrogen after recharge infiltration in almond farms?
So the data we've collected so far is 50-50. So, and that is really because we have really a lot of variability in soils, even if you just look at a 10-acre plot. So typically the way we've set up our experiments is that we have 3 plots that are functioning as a control, and then 3 where we apply recharge. And the soil cores we have collected, half of them show an increase in nitrate and half of them show a decrease. And that can be related to all kinds of factors. So soil type plays a big role. We have very interesting soil stratigraphy. Sometimes you have confining layers that block the water, so it cannot percolate that easily. So then there could be potentially buildup above those layers, and you won't move or remove that nitrate above these layers so easily. So soil carbon plays a big role, and as soon as you have soil carbon, your microbial communities are happy and they will actually start producing nitrate as well. And so the story is really not all that easy, so I don't really have a decisive answer for you.
Fruitful fields for research, further research. I think we're about ready to wrap up, but maybe I would ask each of you in closing to share any advice that you might offer to folks interested in replicating the types of successful projects and activities that you've developed. You might say, don't do it, huh?
I don't know. I'm involved with a community group, also in Davis, which has decided that it wants to try that really low-end kind of a system I was showing you, where you just dig the hole in the ground. They did a system like that in Los Angeles near University of Southern California. They dug out these little planter strips. It cost them, they just did them in a cookie cutter kind of fashion. They cost $12,000 a piece, which by civil engineering terms is very, very small. They did, a whole bunch of them in a neighborhood, and now they're monitoring them to see how well they work. So I don't have the answer for you. I think if you really want to incorporate this in your community, get them built, get them into the development standards, so that at least all of your new development will have this kind of a system.
I think from a grower's standpoint, the communication part is really key. You got to sit down with the folks that are talking about these, because most people have no idea what you as a grower are doing. They have no idea about how long it takes to grow a crop, what it means. And so, because the last thing you want to do, and when we first started talking about these wetlands, I said, well, what happens if some endangered species ends up in this wetland? Is it going to mean then that we have to stop farming around that wetland? And so there are things that you can do. There's safe harbor things to make sure that doesn't happen. And really, that's all part of what we're talking about here is coexisting and doing the best for everything and for everybody. And so, but most people don't think about those things unless you as a grower are bringing them up. And that's really key, really important.
Thank you.
Yeah, I would like to link it back to that urgency. There are most likely going to be less wet years in the coming century. We don't know. We can't really forecast it. So as you're going into the winter into our rainy season, I can only encourage you, if you have a parcel of land that is maybe somewhere connected to a surface water supply system, or where you could potentially capture surface runoff here in the coastal areas, I can only encourage you, try to put some water into the ground. It's really the reliance on surface water supply and surface water storage alone is not going to save us in the future. So yeah, try to become active, try to connect to your water district. Often collaboration with the water district is needed in order to get the water in the winter. And so, yeah, reach out to neighbors and see if you can start something.
If I could add to that, even though a lot of projects, particularly in urban areas, are not big projects, they're still projects, right? If you're only putting a few thousand gallons into the ground from diverting your personal drain pipe to your lawn instead of your driveway, that's still a few thousand acres that's going there and not someplace else. And so it's one of these every little drop counts, right? I heard that before someplace, right?
I mean, I think that that's really interesting, is that the increments add up, and it's so clear because of the urgency and the importance of this. We have to pursue each of these pathways at every scale for us to be successful. So I think that the three of you have really demonstrated that, working at different scales in different settings, that we can make some progress. I would like to thank the presenters and thank all of you for coming, but you guys did a great job.